All right, welcome everyone to episode 7 of Games with Go. Today we will be making Pong. So if you're too young to have heard of it, Pong is one of the first video games ever made, or first sort of graphical video games ever made, and it was one of the first popular arcade games. This is kind of an old screenshot of it. You have these paddles here that the player can move up and down, a ball that bounces back and forth, and keeps score up here. It's basically tennis. You try and bounce the ball back and forth, try to make the opponent miss. So we're going to try to recreate something like this. When they made Pong, they were doing it, I think they weren't even programming. I think they had to actually build it with circuits, so it was pretty tough. But these days, it's something you can do in about a day, or at least get a prototype working in about a day. All right, so we're going to start out with a new folder called Pong, and we'll make a new file called pong.go. And we're going to use our SDL code from last episode as a basis, so you can just copy and paste everything from there into pong.go. And since yesterday, some people who are on Mac OS X mentioned they had some problems. So there's a couple changes here since last week. First, we're calling sdl.init and telling it to init everything. And what this does is it makes sure that the event system is initialized. And then down at the bottom, instead of just delaying for 2 seconds, we have a loop, and we are constantly polling for events. Events are things like input events, mouse events, joystick events. If you don't poll these on OS X, the window doesn't work at all. It's like you have to do this. And then as well, we're checking for the quit event, which can detect when you click the X to close the window, so that you can just close the thing like a normal program. So 2 small changes since yesterday. Okay, so we are going to start. We're going to want paddles and a ball in our game. So we're going to want some types to represent those things. So we're going to want something like this. So the ball is going to have something like a position. So why don't we have a position struct, which will have X and Y. We'll make those float 32s. So in game development, it's typical to use 32-bit floats because they're smaller. You can usually get better performance with them. Also, if you end up using a 3D card, those usually use 32-bit floats internally as well. So this is kind of the normal thing you'll see. So we might want to do something like this, where we have a position. Ball is going to have a radius, so we can decide how big or small it's going to be, and it's also going to have like a velocity in the X and Y directions. So we'll do something like X velocity, Y velocity, something like that. And then maybe we could give it a color too. And we made this color struct earlier with red, green, and blue. And you'll notice that I've got some things here where like the name for the variable is the same as the name of the type. Go allows that. Some languages don't, but you can do that. It's fine. We're also going to want paddles. And our paddles are going to have a position as well. And they're going to have, let's make the size of them configurable so we can give them a width and a height. Paddles are just rectangles. And then we can give them a color as well. Okay, so a quick note about some Go language features around structs. So you'll notice we have 2 different types, ball and paddle, which both have positions. So if you're used to C#, Java, C++, you might be used to the idea of inheritance. So rather than sort of repeating uh, yourself here, remember one of the guidelines in programming is don't repeat yourself. And here we have position, here we have position. And in object-oriented languages that have inheritance, the way you might approach this is you would have something like class entity, and it would have a position, or x and y, for instance. And then you would have class ball inherits from entity, and then it could have its other things like a radius. And class paddle inherits from entity, and it would have its width and height and so on. Whoa, autocomplete. And what happens when you inherit is you get all the things from the thing you're inheriting from. So ball would also have an x and y, and paddle would also have an x and y. So Go doesn't have inheritance, but it achieves a similar thing with something called composition. So this basically gives the ball a position. But it's a little bit awkward to use because if you wanted to say, if you had a ball and you wanted to say ball.x, you can't. You have to say ball.position.x. Extra typing, kind of confusing. But what you can do in Go is if you don't give the variable a name and just leave the type there, then what Go will do is sort of bring this struct inside this one. And so once you've done that, if you have a ball or a paddle, you can just say ball.x. All of the fields of position become part of the fields of ball. And the other thing that happens is if you had a function with a receiver on position, so let's say you had something like this. This is something you might do. You might have a distance from function that you can call on a position, and you pass it another position maybe. So if you have a function that is defined on a position with a receiver type of position, when you do this with a struct, then you can use the same function on ball and paddle as well. So it gets you, it's similar to inheritance in that you get not only the field from position, but you also get all of its receiver functions will work on your types as well. So let's use that. So we'll take the name off position, just take the type for our ball and our paddle. Okay, so now we're going to want to be able to, let's talk about game loops. So most games have a similar, very high-level structure in that there is a game loop. And the basic idea there is you have a loop that goes forever, or until the game or level is over anyway. And there's a set of things you tend to always do in these. One is you get all the input, keyboard, mouse, etc. You update all your things. This would be like physics if your game has anything resembling physics, any AI that's going to happen. So you move your things around, update the health and so on, whatever's going on in your game, and then you draw everything. Nope. So you do this over and over. You get your input, update all your state, and then draw the things to the screen. Often these things are grouped into an update function and a draw function. And the reason you might group things like that is you might want to draw more often than you update, or vice versa, right? If your game needed really precise physics, you might want to update it like 120 frames per second, but only draw at 60 frames per second. Or it might be the reverse. Maybe the physics is pretty simple, and you can do that 10 times a second, but you want to still draw 144 times per second. So at a high level, we're gonna want to do this. We're gonna have a sort of an update section and a draw section in a loop that sort of drives our game. So what we want to do for all the things in our game is give them update and draw functions, so that a paddle can update itself, ball can update itself, and they can draw themselves as well. So let's start off with that. Let's do function going to take a paddle, and we'll do draw. Okay, so how's the paddle going to draw itself? Pretty simple. It's just a rectangle. What we want to do is we want to have the position of the paddle represent the center of it. And when we draw it, we're going to want to draw from the top left to the bottom right. And yeah, so what we want to do is we want to figure out where we're going to start drawing. So our start X position, we're going to want to take the paddle's X position, and then we're going to want to move it over by half the width. So just to draw this out, right, if we have our paddle, this is just a little rectangle, and this is the position, and this is the width, this is the height. We want to start drawing up here and go boom, 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 boom. So that's going to be the fastest way to draw going through memory like that. So we're going to want to, from our position, we're going to want to move over here, half the width, and then up here, half the height to get our starting position. That's where we're going to start drawing. This will be our start X, and we're going to want to start Y. And then the pixels are actual integers, so we're going to want to convert this to an int, because our positions are stored as floats. But in the end, we're going to have to truncate them to ints so we can use them. Now we want to draw a rectangle. So we're going to say for y is equal to 0, y is less than paddle.height, y plus plus. And then for x is equal to 0, x is less than paddle.width, x plus plus. And then all we need to do is set pixel, start x plus x, start y plus y. And then we need to pick a color. So our set pixel that we did last episode takes in a color. Let's just give it white for now. So let's do color 255, 255, 255. And then we also need to give it the pixels to pass. So we're going to need to deal with that. So that means our draw will need to take in pixels. Like that. Okay. Something you might have noticed is whenever I'm kind of iterating through the x, y coordinates on the screen, I'm always starting with y and then x. And it might seem like it's more natural to start with x because we always write out x first. But there's a reason to start with y. And that has to do with going through memory in order. So you might remember from a previous episode, I talked about how CPUs are much, much faster than RAM. And if you are hopping around randomly in memory and you have to get things from RAM, it's very, very slow. You can spend 100, 200 cycles of CPU time waiting for something to get to you from RAM. And since that would never work, CPUs have cache. So that when you ask for one number from RAM, say you ask for this, you'll go ahead and get the next like 64 bytes of memory all at once, right? So you don't just get this 0. If you ask for 0, you get the next 64 bytes as well. The next 64 contiguous bytes in memory. So if you can go through memory in order, you can go much, much, much faster than if you hop around. So if you were to iterate through x in the outer loop and y in the inner loop, if you imagine this as a 3x3 screen, 3x3 pixel screen, you would be going here, and then here, and then here. So in your array, you'd be going to 0, and then to 3, and then to 6. Then you'd be going back to 1, and then to 4. So you're hopping around in memory. You're going to be missing the cache a lot. It's going to be a lot slower. Whereas if x is in the inner loop, you're going 0, 1, 2, 3, 4, 5. So you're going absolutely in order, and you're going to be in the cache almost all the time. So You always want to keep that in mind, especially in the inner rendering loops of a software renderer, because software renderers are not fast. Even on modern computers, screens have a lot of pixels, so you got to pay attention. Okay, so this should draw us a paddle. And then let's also do one to draw a ball. Let's keep the ball functions near the ball. This is going to need pixels as well. All right, so so drawing the ball, we're going to do something that is probably not optimal from a performance standpoint, but it will be pretty good. So what our approach is going to be, we're basically trying to draw a circle that's filled in. And to do that, what we're going to do is we're going to iterate over a square, right, where this is the radius of the circle. We're just going to iterate over the whole square. And at each pixel, we're going to see if the distance to that pixel is within the radius, right? So around the edges, this is our circle, we're going to be too far, so we're not going to draw it. But if we are equal to or less than the radius, then we're going to fill it in. All right, so it's a little bit of extra work because we're iterating over these pixels that we're not going to draw, but it's very simple to do, and it will be pretty fast, so we're going to stick with it. And there's a principle here you'll hear in programming called YAGNI, which stands for "Ya ain't gonna need it." And this is just sort of a warning that if you start trying to go too deep into something too early, it can be a mistake. For instance, we could go dig into Bressenham's circle drawing algorithm, modify it to draw a filled circle. We could spend a couple days optimizing it, making sure all the edge cases work. We might do all that work, and then maybe the next day we decide, hey, you know what? We don't want to draw the ball. We actually want to load a bitmap from file and just draw the bitmap, right? And then we would throw all that work away. It will have been wasted time. So we'll start out with something simple. If later we decide we need to draw, we want to do like crazy Pong with like 500 balls being rendered at once, and then maybe we could try to optimize it some more. So we'll start out with something simple. We're just going to iterate over the rectangle, the size of the radius. So we'll start at negative radius to positive radius, basically. Same for x. Negative to positive radius. Because again, our position is going to be at the center of the ball, right? We're going to start, the position is going to be the center, so we're going to start at left 1 radius and up 1 radius. And then we're going to check the distance. So we're going to say if x times x plus y times y is less than ball.radius times ball.radius. And what we're doing here is we're avoiding having to do a square root, right? So we're keeping both sides squared because a square root is an expensive instruction on a CPU. So we're just not going to do it because we don't have to. Then we will draw pixels. So we got to convert to integer. So we take the current position of the ball plus the x, the current position of the ball plus the y, and then need a color again. We'll just stick with white for now, like the original. And then our pixels array. All right, what are we unhappy about? Oh, comma. Should be a semicolon. Okay, so now we can draw a ball. We can draw a paddle. Let's actually test this out and see if it's happening. So this is going to be our game loop. Right now we're already checking for events. We're checking for the quit event. And I put a little delay in here just so that your CPU doesn't completely heat up doing nothing at all. So let's try it. Let's try drawing a paddle. Well, actually, we'll draw it outside the game loop for now because we only need to draw. No, we'll just do it here. We'll just keep drawing it. So we'll do. Oh, we need a paddle. So let's make a paddle. So we'll do player 1 is equal to paddle, and it needs a position, so we'll just put it at 100, 100. And what else? We need a width. How big should our paddle be? Let's try 20 wide, 100 tall. And oh, did we give it a color? We did. So color should just come from ball.color, and paddle will come from paddle.color. And then we make the color in here. Let's see if is that correct? So paddle's got a position, width, height, and a color. Position, width, height. Declared not used, that's fine. And we need a ball is equal to ball, position, put it somewhere near the middle. We'll give it a radius of 20 and make it white. Okay. Oh, we need the x velocity and y velocity, so we'll make it motionless for now. Okay, and we'll do player1.draw and ball.draw pixels. Let's go and see. Okay, someone asks, why does ball.draw use a pointer receiver instead of a value receiver? So right here, for instance, because this is not mutating anything, it would be perfectly fine to pass ball as a value. So you could pass it like this. That would copy all the contents of your ball into a new ball that the function would use. And you're absolutely right, that would work fine. It is it is going to be a little bit better performance, probably, to pass a pointer since you're only passing one thing. It could be the case that it is faster to pass it as a value because there might be less memory allocations in that case. The ball might always stay on the stacks and never go on the heap. That's something you kind of have to test to figure out. I mostly just do it as a pointer because that's a nice default. If you kind of always do things as a pointer, unless you really need to not, it's less confusing. And like if you were doing this in Java or C#, for instance, like it would always be a pointer, unless you made it a struct in C#. So yeah, no particular reason. And if you're trying to like adhere to functional programming principles, you might prefer to do it this way. Yep, no problem. Okay, and by the way, speaking of functional programming principles, we're doing that a little bit here. You notice we're taking in the array of pixels that we're going to draw to. Another way you could do this is you could make a global variable for your pixels, right? And then you wouldn't have to pass in the pixels. And then you could just use the global variable. One advantage to keeping things functional, and what I mean by that is that this function has no side effects other than a thing. Yeah, actually, this function has no side effects at all. And what that means is if a function only uses the parameters that it gets passed and it doesn't change the state of anything outside of itself, that makes it a pure function, which means it has no side effects. And the good thing about that is if you need to test things, if you pass this function the same values or the same pointers or whatever, if you pass it the same things, then the result will always be the same. So writing tests or thinking about its behavior becomes simple. And it's a good idea to make functions pure whenever it's not too hard to do so. Especially with game programming, it can be bad to try to do that strictly all the time. It can end up being more trouble than it's worth. And there can be performance considerations too. And you can't hurt performance too bad with games. But when possible, it's good to think about, hey, can I design things such that every time I call this function with the same things, so the same thing's always going to happen, right? It's not modifying a global variable anywhere, right? So and you get some other advantages like that. Like because we pass this, the pixel array we want to draw to, if we wanted to have a crazy Pong that drew to 10 different windows and 10 different frame buffers, it's ready to do that. Okay, so what were we doing? We were trying to see if we could draw. Let's see if we can do it. Nope, we still have our old crazy gradient here from the test. Let's get rid of that. We won't draw that anymore. All right, we don't have anything. Okay, and the reason why is we need to move this stuff into our game loop. So we wrote data to the pixels array, but we did not update the SDL2 texture and copy it to the renderer. So let's move that down there. All right, now we've got a paddle and a ball. Good start. So now we know we can draw these things. Let's see if we can start updating them. Let's just do the ball first. We'll do an update. And then what we'll do here is we'll just say that the ball.x plus equals ball.x velocity, and ball.y plus equals ball.y velocity. And if you haven't seen this syntax here before, this is equivalent to ball.x equals ball.x plus ball.xv. It's just shorthand for this. And you see this in lots of like the C syntax languages, so you can do this in C. And Java as well, I think. Okay, so that's pretty much all that's going to happen with the ball for now. We're also going to have to handle collisions because the ball needs to bounce around the screen. Why don't we go ahead and do that now? So at least part of it. So if the ball goes, let's go to the, if the ball goes past the edge of the screen, that's going to be like a point. But if it hits the top, it just bounces off the top. So let's handle that case. So if ball.x is, or ball.y is less than 0, so that would be the top of the screen, then we want to reverse the velocity of the y component. So ball.yv equals negative ball.yv. Else, if ball.y is greater than when height ball.yv so what this should do, why are we unhappy? Oh, so we need to make this a int. Okay, so this should handle if the ball goes up to the top of the screen, it's going to reverse its y direction and come back down. If it goes to the bottom, it'll reverse its direction and come back up. All right, then paddle. Okay, so paddle actually needs to respond to input. So we need to get some input and feed it to the paddle. So there's a couple ways to get input out of SDL2. You'll notice here, this is our event loop. And you'll notice this weird switch statement here. I don't think we've introduced switch statements at all yet. This is a special kind of switch statement called a type switch. So this loop, each time through the loop, gets an event from SDL poll event. And the type of the event is not totally decided yet, right? It's an event interface. It's some kind of event, but there's different types of events it could be. And what this type switch does, this dot type syntax, is it will let you check each possible case of type that event could be and do something different. So in the case of an SDL quit event, then we just quit the program. But you could also check for SDL.keyboard event and then start doing things based on what the keyboard event has in it. But there's a different way to use keyboard input that's a little bit more convenient, I think, in this case. And that is, there is a thing called get keyboard state. So we can say key state is equal to SDL.get keyboard state. And what this is an array that SDL manages internally. And when we call get keyboard state, we just get a pointer to that array, right? Or this becomes basically a slice in Go that points into SDL's own internally managed keyboard state. And every time we pull the events, this keyboard state array is also getting updated. And basically what it contains, it's basically an array like that has a representation of every key. So, you know, A, B, C, D, escape, up arrow, down arrow, and so on. And whether or not it's being pressed right now, or as of the last time you check the event. And so what we could do is we could just pass that key state to the paddle, and then the paddle can check it out. So paddle, so the keyboard state is just an array of bytes, or uint8s. So say key state uint8. And then the way that you check stuff in there is SDL has a bunch of constants built in to refer to the different keys. So for instance, if you want to see if the up arrow key is being pressed, these all start with scan code, and then underscore, and then from there it's pretty much intuitive. The up arrow is up. Oh, I see we have some questions. 1 second. Someone is asking if the event.type is an expensive call. Yeah, I do not know how expensive it is. I do not think it's like as expensive as reflection is in Java and C#. Yeah, someone else says they're unfamiliar with the syntax. It is a weird syntax. It's just like a special built-in variant of the switch statement built into Go. You can actually do more with it. You can do this. You can name this whatever you want, right? So you make a variable, right? And then inside this switch statement, this will be the type that particular event was, right? Which then lets you do things with it. So then at this point, the event is a quit event, and the only thing the quit event has is a time state or a type. Or if it was a keyboard event, then in here, the event is a keyboard state event, and you have all the keyboard stuff in there. Yeah, it's pretty cool. But yeah, I do not know how expensive it is, and that's a good question. If you're having to do that a lot, you'd want to test to figure that out, and if it's too expensive, you need to find a different way to do it. All right, so these scan codes. To find out like if a certain key is pressed, you just refer to the key state, and as the index, you pass it one of these scan codes. So if you want to know if the up arrow key is being pressed, you give it SDL.scan code up. All right, and that just is a number. It's just a constant number that indexes into the proper start of the key state array, and that'll either contain a 0 if the key is not being pressed, or not 0 if the key is being pressed. So if we want to know if up arrow is being pressed, we just say if key state SDL.scan code up is not equal to 0, then we know the up key is being pressed. So we could do something like move the paddle upward. And then if key state SDL.scan typo code down is not equal to 0, then move the paddle down. Okay. Something to keep in mind here too, if you're looking at documentation for SDL or looking at tutorials online, you'll actually see this looking more like this. Everything's got SDL pre-appended to it in the SDL library because it's a C library. And when you import the header files for a library, you get all of the functions and variable names just available to you immediately. So like C libraries will always have the name of the library kind of prepended to every single variable. Because Go has the package import system where you have to type SDL dot anyway, the people who wrote the bindings removed the SDL prefix because it would be redundant and extra typing. So when you're looking at documentation, just keep in mind that you can remove the SDL, right? So if you look at the docs for this, it'll be something like this, but skip the SDL when you're in Go. Okay, so let's give this a try. We don't need the event. Let's get rid of it. Okay, so now if we want to update the player one paddle, we need to call update and give it the key state. Okay, so let's give this a try. All right, so you notice we have a bug. The paddle's just getting longer. So what's happening is we're successfully updating the position of our paddle, and we're successfully drawing the new paddle right here. But we have not erased the old paddle, right? So we're just drawing into this pixel array, and the old values are still there for where the paddle used to be. So what we need to do every frame is clear, basically clear the whole screen. Yes, we made snake. So let's just make a quick utility function to clear the screen. We can put that, I'll just put it under here. We'll do clear, and this will take a pixel array. And then we will just do for I, arrange pixels. I think that is all we need to do. So this will just clear the entire screen. And you could try to be more efficient and only clear where the paddles were and stuff, but this is actually really fast because it goes through memory in order, and it's always going to work. So that is a good place to start. So before we do any drawing, we're going to want to do clear everything. Get a flat, blank slate. Also, let's keep our updates and draws separate. All right, let's give it a try. All right, we can move stuff now. It's almost feeling like a game. All right. So next thing we need to do is we need to start moving our ball. We also need to handle the case when the ball goes off the screen. So for now, let's keep it really simple. Let's say if the ball.x value goes off the screen. You know what? We can simplify this. Since we do the same thing in each case, we will use the OR comparison. And we'll just do it like that. So if the ball goes too high or too low, we'll switch the position. And we'll do the same thing here. If the ball goes all the way to the left or all the way to the right, this needs to be integer. Where'd I go? There we go. then that'll be like a point has been scored, so things will reset. So we'll put the ball back at its original position. What did we say? 300, 300. We'll just do it like this for now. Okay. Then let's get the ball moving so we can see it happening. So let's give this some velocity. 10, 10. Let's see what that looks like. Oh, looks like nothing because we are not updating the ball. All right. We see our ball bouncing around. Let's slow it down a little bit. All right, so one thing we notice is that the ball is not bouncing until the midpoint of it has hit the boundary. So let's fix that. So we'll adjust for the radius. Need to make this an integer again. All right, that looks better. Okay. So let's start adding. Oh, someone asked if there's past episodes archived somewhere. Yes, you can go to the gameswithgo.org website, and there's a link to past episodes there. There's a link in chat, but if you're watching this on YouTube later, just go to gameswithgo.org, and there's a link to the YouTube archives. Okay, let's add the player 2 paddle, so we can start bouncing the ball back and forth. Let's make this start on the other side of the screen. Same size, same color. And for now, let's make this a computer player. So we can call it AI update for now. It's not going to need any keyboard state, but it does need to know where the ball is. So let's take in the ball. Now here's a really simple AI that's completely unbeatable. Pretty clever, huh? So this paddle is just always going to be at the same position as the ball. It's going to be impossible to defeat, and it's only one line of code. I think that's pretty fun. So player 2, we'll get the AI update and the position of the ball. Uh-oh, where is he? Did we go too far? Oh, we're not drawing him. All right, we can see he's tracking the ball perfectly, but the ball still passes through the paddles. So let's handle collision with the paddles. Also, let's think about where exactly do we want the paddles to go? Maybe we can go a little further to the edges, something like 50, and then we'll do window width minus 50, so they'll be in the same spot. Can we do that? Make that a float. Okay. All right, let's make the ball bounce off them. So ball.update. So it's going to need the paddles. So we need to have paddle 1, paddle 2, All right, so we need to get the position of the paddle and then move out half the width to know when the ball has hit the outer extent of it. So if the ball is to the left of that on paddle 1, here let's call these left paddle and right paddle. That'll make it more clear. Then we want the ball.X velocity to reverse. What's wrong here? Oh, X. It might have been the right thing just to keep everything integers all the way. We can evaluate that later. Okay, so that'll bounce it off the left paddle. And then for the right paddle, similar idea. Except see if it's greater than. I don't think Go will let us do it that way. Can I put it on the next line? Yes. Okay. Oh, but this is just going to bounce anytime it gets to the. We have to make sure that the paddle's actually high enough. So let's actually keep these separate for now. So we'll check left paddle. This should be left paddle. All right, so this tells us that the ball is at the same X position as the right edge of the left paddle. But now we need to see if the ball's Y position is greater than paddle.y minus paddle.height over 2. Right, because this is going to be the top of the paddle. The ball needs to be lower than that. And the ball needs to be higher than paddle.y plus paddle.height over 2. Ball needs to be higher than the bottom of the paddle. And if that is the case, then ball.x v is reversed. And we probably need to do some integering here. Oh, no, we just need to move this up. Paddle has no method Y. Paddle has no method Y. Left paddle. And now we need the integer. All right, and we'll use the same logic on the right paddle. Okay, let's give it a try. Oh, okay, so ball to update needs the paddles now, so we haven't given it that yet. So we need player 1's on the left, player 2's on the right. See if we can bounce them. All right. Oh, I'm going to lose. I'm losing. I've lost. My paddle is too slow. And the computer can move faster than me. It's cheating. It's got hacks. Let's see if I can hit it. Oh, I just missed it. All right. Let's make my paddle faster. Paddle. Let's make it 5 times faster. There we go. All right, we can play. Cool. Okay, we have got a working prototype. And we're approaching the end of the hour. So I think we're going to stop here, but let's talk about some of the things that we still need to do. So we can see the ball doesn't bounce until it's halfway in. So we need to adjust for the radius of the ball when it bounces off the paddles. The original Pong also had a game mechanic where if you hit the ball with the middle of the paddle, it'll bounce as it is now. But if you hit it on the edges, it would change the angle of the ball. And that gave you some like gameplay stuff. If you hit it with the edge, the ball would move a lot differently, and you could try to aim it to make it miss your opponent's paddle. And it had like 8 different segments. So we can work on that. Also, we need to be able to keep score, so we need some way to draw the score onto the screen. And also, we have currently there's the frame rate is just however fast your computer is minus this delay of 16 milliseconds. Ideally, we should be able to let the frame rate be as high, or at least high within some limit as a player's computer can handle, but have the paddles and balls move at a constant speed relative to time. So we need to make the frame rate independent of the physics, in a sense. So that's something we need to think about. So let's just sort of make a list. We need frame rate independence. We need score. We need some sort of like game over state where you win or lose. We might want to let people play 2-player versus playing the computer. Right now you can only play the computer. The AI needs to be more imperfect. Right now the AI can never lose. That's no fun. Let's see. What else? There's lots of things we could consider, such as handling resizing of the window. Right now we're hard-coded to 800 by 600. So you can see that it's actually pretty easy to get a basic prototype running. There's not a whole lot to it. But once you start considering things like being able to handle a computer that runs at any speed, slow or fast, handle any size or shape of the window, figuring out how you're going to deal with that, handling players and AI. Right now we only handle keyboard, so should people be able to play with a mouse? Should we handle joystick? Right, there's lots and lots of stuff you have to do to like refine things to really make it a real game. So next episode we'll maybe tackle some of these things. I think we'll do the joystick for sure. Maybe we'll work on making the AI imperfect, and then maybe keeping score. And if if you want something to play with between now and next time, you might think about how to do this. How would you draw the score on the screen? There's a couple approaches to that. We don't currently have a font library available to us. There are some, but there's some other ways you could do it too. And you'll notice the original Pong did not have a font library either. They were just hacking it in there. So that's one way you could do it. All right, before we go, does anyone have any questions, comments, or concerns? I want to try one thing real quick since we have like 5 minutes. So feel free to ask questions if anyone comes up with something. I'm going to do a little experiment here. Let's see. Now, I'm gonna leave this for later. But what we're gonna do, we might do next time, is we can do a kind of cool like pseudo 3D effect on this ball. And something else we could think about is, do we want to like load bitmaps for our paddles and ball, so we can have fancier graphics rather than just drawing rectangles. All right, someone's asking if the code is online. The code is kept in a GitHub repo. I do ask that people contribute. If you go to gameswithgo.org, there's a section where you can contribute via PayPal, and people who contribute get access to the source code repo. Otherwise, you have to follow along and type it in yourself from the streams. All the videos are archived, so if you couldn't keep up today, you can always go back and see it that way. All right, that's it for tonight. Thanks everyone for joining. Next time we will choose some refinements to do on Pong to make it a little bit more like a real game. And I think coming up after that will be some procedural generation stuff, which will be I think it's pretty fun. I've been preparing for it. It's going to be cool. All right, good night everybody.